Main. Let me think. So I think I'll turn this on for now. Settings. This one. We're good there. Let me share my screen. All right. So welcome, scholars. I have that it is officially that time for us to get into the material. All right. So we're essentially in the home stretch. All right. We've completed chapters 1 through 3. All right. And so today we're going to be moving into chapter 4 on integration. The simplest way I can, let me get this student. So the simplest way I can summarize integration. So with chapters 1, 2, and 3, basically we were exploring, the derivative and what it is, a derivative. So given a function, we'll take the derivative, it'll produce a result. So now with integration, what we're going to do is start with that result and explore different techniques to, given the result, how do we work backwards to get back to where we started from? So that's essentially what integration is. All right. So again, we're starting with the answer and then exploring techniques and methods for working backwards to get to where we started from. So this integration is essentially the inverse of differentiation, right? Okay, so let's take a look at it. So we'll start off with section 4.1, anti-differentiation. A few objectives here. 1, find an antiderivative of a function. 2, evaluate indefinite integrals using basic rules of anti-differentiation. 3, use initial conditions to determine an antiderivative. So we have this theorem 1, the antiderivative of f is a set of functions f of x plus c such that d by dx of the antiderivative equals f of x. Okay. The constant c is called the constant of integration. The set of functions so that when we take their derivative, it gives us f, right? Anti-differentiating, I can barely say that word, anti-differentiating is often called integration. To indicate the antiderivative of this function is going to be x cubed over 3 plus c. We write the integral of x squared dx is x cubed over 3 plus c. And again, we're going to explore how do we calculate something like that, where the notation integral of f of x dx is used to represent the antiderivative of f. More generally, the integral of f of x dx is going to be the antiderivative f of x plus c, where the antiderivative of f of x plus c is the general form of the antiderivative of f. Okay. So it's just kind of laying the stage. Determine these indefinite integrals, that is, find the antiderivative of each integrand. Okay. So I just did this just a moment ago. All right. So the antiderivative of 8, right? So what function, when we take the derivative, gives us 8, right? I think that's going to be what? 8x plus some constant, right? The derivative of 8x, right, to check it, the derivative of 8x is what, 8? Or 8 dx? And the derivative of a constant goes to 0, right? So the integral of 8 is going to be 8x plus some constant, okay? So that one's not too terribly bad. And again, when you get your result, generally speaking, you just check it by, you take the derivative and you should get back to your f of x. Okay? So now we want the integral of 3x squared dx. So 3x squared. Normally if we have like the derivative of a power, the power comes down, right? And we subtract 1 from the power. So then the antiderivative, Tatum and Ford. Tatum. So the antiderivative is similar. When we go to find the integral of this guy of x squared, we add, instead of subtracting one from the power, we add one to the power. Let me just show you this real quick. So if we think about x squared by itself, if we just add one to the power, we'll get what? X to the power 3. But if we take the derivative of this guy, we're going to get 3x. Let me think. Over 3. We're missing something there. Hang on. Oh, yeah, no, we're good. We're good. Right? Now, if we just added one to the power, we would get the x squared would become x cubed, right? But this guy, if we take the derivative, we'll get 9x squared, right? But it's supposed to be 3x squared, so there's an extra term. So really, when we take the integral of a power function, we got to say if the new power is power 3, we got to say divided by 3 plus some constant. So then after we simplify, we'll get x cubed plus c. And again, if you check by taking the derivative. So we actually had the right answer first, but I drive home the fact that we do still need to divide by 3, right? So it's going to be x cubed over 3. So then the integral of the original guy should just be x cubed, right? Because when we take the derivative, we're going to get 3x squared. If we had, if we didn't divide by 3 and we take the derivative, we're going to get the wrong thing, right? So we needed an additional term. Okay. Okay. And again, with these, whenever you get an answer, you just check by taking the derivative. The derivative of this guy is just 8 dx. The derivative of a constant is 0, so we're in the clear. The derivative of x to the power of 3 is going to be 3x squared, so that checks out. And again, the derivative of a constant is 0, right? So then it'll bring us back to here, okay? With e is its own derivative, right? So we might try, its integral might be what? E to the x, and I think we're good, plus some constant of integration. Okay. And then again, just check by taking the derivative. Now, I think so we would normally divide by that power, but I think if we take the derivative here, we're okay. The derivative of e to the x is e to the x dx. And again, when we take this derivative, it goes to 0. So we're okay there. Okay. Let's see. Dx over x. So I think that's what? ln of x plus c. The derivative of ln is du or dx over x, right? So I think we're clear there as well. I think there's a little bit more to the narrative there, but for right now, this will suffice, right? And again, with each of these, just check by taking the derivative. You should get back to your f of x, right? The part in front of to the right side of the interval, okay? And I think we have a type version of what we just experienced. 8x plus c, because when we take the derivative, we get that. X cubed plus c, so I think we got all of these correct. Okay. All right, let's keep going. So we have this theorem too, basic integration formulas. So how do we take the integral of some basic formulas, right? So the integral of a constant dx is going to be kx plus c, right? So where k is a constant. So like if we had the integral of 2, that integral is going to be just 2x, right? Again, whenever you integrate a constant, it's going to be that constant times x plus some c. The integral of a power, or x to some power, is going to be x to the power of r plus 1 divided by r plus 1 plus some c. And we saw this is where we basically had that additional 3 so that it would work out properly. If you were to forget this part here and then you check it, it's going to be a little off, right? So you always check by taking the derivative whenever possible. To integrate a power of x other than -1, increase the power by 1 and divide by the increased power. Okay. Let's see what else we got. The integral, so 1 over x, I think that one is natural log. That's like dx over x right here. So we have x to the minus 1. That's the same as dx right here. That's the same as dx over x. And the integral of that guy is going to be the natural log of x plus some constant, as long as x is positive. If x were negative, then it's going to be the natural log of absolute value of x plus some constant. Okay. We do. Generally, we assume that x is positive. Okay. And then the integral of an exponential is itself, right? So a to the x is itself. But then we also need to divide by the derivative of that power, or divide by a, right? So if you have this a in front of the x, we need to divide by a. In the example that we worked earlier, our a was 1, so that's why we couldn't notice it. The coefficient just persists, and we divide by whatever this a is there. Okay? Plus our constant of integration. Okay? All right. So use the power rule of antidifferentiation to determine these indefinite integrals. Okay? I think we got this. So then x to the power of 7, what are we doing? Adding 1 to the power, right? And dividing by that new power. So a should be x to the power of 8 over 8 plus some constant. And then just check by taking the derivative. I'm going to change this. Give me just a moment, because that totally distracts me. Settings. I think he was here already. Make sure. He probably just like switch devices. That happens a lot too. It looks good. But I do like to, because it distracts me when people start changing devices. It's not a big deal. Play. Let me just turn this off. I got enough people, and I'll check again in like a few minutes. I usually do 2 waves. You know how I do it. Anyway, so say we get this result, and again, we can check by taking the derivative. Right. So if we take the derivative, the 8 comes down and they'll cancel. We subtract 1 from the power, we get a 7, and the derivative of a constant is 0. All right. So it's a quick check to confirm that that works. Okay. Let's work on B. So we add 1 to the power. That integral should be x to the power of 100 over 100 plus some constant. Okay. C. Let me see. So the square root of x is the same as x to the power of a half. And then if we apply the same technique, that's going to be what? X to the power of 3 halves over 3 halves plus some constant. So if we, flip and multiply? 2 times the square root of x cubed over 3 plus some constant. All right. And then D. And it, again, that is the same as x to the power of 3 halves. If we take the derivative, the 3 halves comes down, it's going to cancel to 2/3. Then we're going to have x to the power of a half. And I think we're good to go. And then for D, so this one is the same as x to the power of a negative third. So then if we just add 1, we're going to get x to the power of -2 over -2 plus a constant. So then, we can write it as -2 over x squared plus some constant. All right. No. Sorry, that's not right. That drops down. This is a 1 here, and there's a 2 there. Yeah, that's better. Now this dehumidifier has been off all day. They want to wait until I start teaching to start screaming. Give me just a minute. Siri, turn the heater off. Just to minimize some of this background noise, all these little devices running. Okay. And again, if anything isn't clear, just stop me, like unmute yourself to get my attention or type in the chat and we can talk about it, right? Okay. So these were examples on using the power. Yes.
So for C,
Mhm.
I'm not understanding how you got 3-2.
Three.
Did you add?
Yeah.
Did you add one?
That's exactly what I did, right?
Okay.
Yeah, because
Okay.
square is the same as, and this is missing the integral. It's supposed to be an integral here. So, x to the power of a half, and then you just do the same thing we did with all the previous. Add 1, divide by that new power.
Yeah. Okay, thank you.
Let me check my attendance one more time. I think you guys are good. Nope, glad I checked it. Get the student. That's the only Scott I have. Let me check one other thing. Okay, that looks good. We did lose somebody. I'm not going to make a big deal about it. We are missing one, but that's not a big deal. Let me mark everybody else as absent. And I'll be updating grades and things over the next couple of days. Yeah. So, and it's just for so you can have some feedback, so that you can see what I see, and so we can be on the same page. Okay, let's keep going. Let me see. I think x to the 8 over 8, 100 over 100. Two-thirds x to the 3 halves plus c. That's fine. Right here. Negative 1 over 2x squared plus c. I'm just going to say that caught it. Okay, let's keep going. Quick check I leave as an exercise for you. And here, determine the indefinite integral. Okay. So let's do this. So the integral of e is itself, right? We're going to say it should be e to the 4x, but then we need to say divided by 4, right? Plus some constant. And if we do a quick check by taking the derivative of e is itself, then we have to say times the derivative of the power. So that's going to be times 4 in this case. The 4s are going to cancel. And the c, when we take the derivative, is gone. So we can be confident with this. And again, just check by taking the derivative. So e, yeah, there it is. Let me kind of read. So I want you to see this. So determine the integral. Since we know that the derivative of e is itself, it's reasonable to make this initial guess that the integral of e to the 4x might be e to the 4x plus c. But this is slightly wrong, because when we take the derivative, we get 4 times e to the 4x. And so we have that extra 4 in there, right? So we modify our guess by inserting 1 over 4 to obtain the correct antiderivative. So we have our e to the 4x divided by 4. So that way, when we take the derivative, we finish with what the function that we were left for, e to the 4x, right? Okay. That is an exercise. So properties of antidifferentiation. Property 1, the integral of a constant times a function dx is going to be the same as the constant times the integral. So when you're taking the integral and you have a constant times the function, you can just move that constant to the left side of the integral and then just focus on what's remaining. Whatever answer you get, just say times that constant. Okay. The integral of a constant times a function is the constant times the integral of the function. Property 2, the integral of the sum is the same as the sum of the integrals, or the integral of the difference is the same as the difference of the integrals, right? So it's almost as if you can like distribute this integration across this guy, right? So the integral of a sum, we can break it apart into the sum of the integrals. And you can do a similar argument for the difference. The integral of a sum or a difference is the sum or the difference of the integrals, right? Man, we like are blowing through this section. So we might actually finish this section early. I think our goal for today was just this section. So with the extra time, we'll go through some homework questions associated with this. Determine these indefinite integrals. Assume that x is positive. Okay. So again, the integral of the sum is the same as the sum of the integrals. You could break those up into 3 separate integrals and just work them. And then whenever you have that constant, you can move the constant to the left side of each integral. So for instance, the first one is really just the integral of x to the power of 5. All right. I guess let me go ahead and write out those changes that I'm referring to. So again, it's essentially like we're distributing the integral sign, and I'm going to move the constant in front. So we can rewrite this as 3 times the integral of x to the power of 5 dx plus 7 times the integral of x squared dx plus, we'll just leave it as the integral of 8 dx, right? So the integral of x to the 5 should be what? X to the 6 over 6. So we're going to have 3 times x to the 6 over 6. For that. Now, normally we're going to say plus c, but we can combine all the c's at the end. So the next one, x squared, is going to become x cubed over 3. And the integral of a constant is going to be that constant times x. And then all the c's from the first, second, the c's from all 3 components, we can just, there's some number here, some other constant. All right, we're just going to sum it up like that. And we can simplify this a lot. So that's going to be x to the 6 over 2 plus 7x cubed over 3 plus 8x plus some constant. Okay. So then again, you can check by, if you take the derivative, the 6 comes down, that's going to become a 3, and the powers now are going to become a 5, so you got 3x to the 5th, that checks out. The next one, if the 3 comes down, we're going to have 7x squared, that checks out. The x is gone, that checks out, and the derivative of a constant is 0. All right, this guy's going to go to 0. So then, okay. I think for B, I'm more inclined to distribute, since we're dividing by a monomial, whenever we're dividing by one term, we can essentially distribute that across the numerator, right? So we can rewrite this integral as, that's going to be 4x to the negative 1. Okay, so that's something there. Plus 3. Let's see, plus 2x cubed. Okay, we're going to say dx. So then we can rewrite this 4 times the integral of dx over x is the first one, plus the integral of 3 dx, plus 2 times the integral of x cubed dx. All right, so those are the separate integrals. So then if we evaluate each one, the integral of dx over x is natural log of x. So that should be 4 times the natural log of x. Okay. The integral of a constant is that constant times x, so that's going to be plus 3x. And the integral of x cubed is going to become x to the 4 over 4. Right, so then 2 over 4 becomes 2. And if you combine all the constants from each of those, it's just going to be plus some other constant. Okay. And then we would check by taking the derivative. For the sake of time, I'm just going to go with it. Okay, so I think I'll just copy. I'll get a copy of each one. So let's just copy. It's pushed. And I'm just going to do a side by side. Delete, right? X to the 6 over 2 plus 7x cubed over 3 plus 8x plus a constant. Okay, so that one checks out. Cut. Paste. 4 natural log of x plus 3x plus x to the 4 over 2 plus a constant. Okay, so they both check out. Okay. Then I'll leave this as an exercise for you all. Let me check let me see if I got any stragglers. I think we're looking good. Okay. So I only have one unaccounted for. Go like this. Does this work? Let's go like this. Yeah, it's not too terribly bad. Oh no. Okay. Let's keep going. So find a function f such that this is the case. Let me see. Okay. So basically what they're asking us to do is to take the integral of x squared dx, right? So let's do that. Let's see. So that should be what? X cubed over 3 plus some constant. Okay. Then they also give it, so we're saying that right now f of x is showing as x cubed over 3 plus a constant, but then they gave us additional information that when x is -1, y is 2. So then f of -1, which is going to be -1 cubed over 3 plus some constant equals 2. Keep working over here. Okay. So we get a -1/3 plus c equals 2. So then ultimately c equals 2 plus a third. 2 1/3, 6. So 7 over 3. So then it looks like our function takes on the form x cubed over 3 plus 7 over 3, right? Nope. Let's go like this. Let's put you here. About there is good. I want to copy. And I'm going to get rid of all of this. Okay. Right. So that way, when we take the derivative, right, the 3 comes down, and they cancel, so we have x squared. The derivative of a constant is 0. And when x is -1, we get a -1/3 plus 7/3 is 6/3, which is 2, right? So this satisfies both initial conditions. Okay. Let's try another one. X cubed over 3 plus 7 over 3. X cubed over 3 plus 7 over 3. Okay. All right. And so that brings us to the end of section 4.1. So I will go ahead and save section 4.2 for Wednesday. And so with the remaining time we have today, let's work through some problem sets. Let me change this view. Seamless. And I would like an additional page. Add a page. There we go. I think we're cooking now. Okay, so let's pull up the assignments associated with this section. Kind of minimize. Come on. Full tabs is fine. My math lab is here. Allow. Sign in. Allow. Okay. All right. So we're here for calculus for business. So again, this is the last chapter, right? This is the last of the new material. The original goal was to make it through chapters 1 through 4, and we're pretty much on track with as outlined in the syllabus, right? 2, 3, 4, 5, and 6, right? So this is week 11, 12, 13. I mean, that's essentially it. Like once you hit week 13, then you're trying to wrap up. So it looks like it's only essentially 3 weeks of new material remaining, right? At about a section a day. So 2 sections per week. All right. I know the rhythm was kind of intense initially, but we finally got past that. The hump, right? The heaviest part. So it's a lot more lax now than it was originally, right? And so you can see, as far as the new content, again, it's about a section per day from here on to the end. So after today, it's only going to be 5 more sections of new content, or 3 weeks of material. Then we're going to be reviewing for the final from there on out. Hey, Google, give me a random number between 1 and 24. 9. Okay. Let me do this here. Come on. Give me, oh, come on. That's not going to work. Give me, oh goodness, random number between 1 and 24. Okay, and the first one we got was 9. So we'll do 9 first. Maybe we'll go to 4. So number 9. Okay. So we're asked to find the integral. I'm going to shrink this down to about this size. That's decent. Okay. And this is question 9. This comes from section 4.1, question 7. Basically, take the integral. We got this x squared minus 7x plus 3 dx, okay? Now, again, I could break this apart into 3 separate integrals. I'm just going to jump to the answer. Okay. So if I integrate that first term, it should become what? X cubed over 3. The next one is what? X squared over 2. And the last one is going to be 3x plus some constant. Okay, so then I think I'd rather just use my keyboard for typing this. All right. Settings. Want this off. Okay. All right. So the first one. Maybe it's not working. Okay. Let's do like this. Okay. So we got x cubed over 3. X cubed over 3 minus 7x squared over 2 minus 7x squared over 2, okay, plus 3x plus c, plus 3x plus c, and let's do a capital C. I don't think it really makes a difference, but okay. Okay. So let's go to question number 4. Okay. So given this, find dy by dt. Okay, so given y in terms of x and x in terms of, well, it's supposed to be x in terms of t, but we'll work with what we have. Okay. This is what, question 4? And this comes from section 3.9, question 3. Okay. So we're given that y equals 7x squared plus 5x. We're asked to find the derivative of y with respect to t. Okay. When x equals -1 and dx by dt equals to 4. Okay. So if we want the derivative of y with respect to t, and they gave us the derivative of y with respect to x, so what we can do is find the derivative of y with respect to x, and then we're going to say times the derivative of x with respect to t. Okay. So let's find the derivative of y with respect to x. Let me see. So essentially just take the derivative on the right-hand side. So that's going to be 14x plus 5. So that's our dy by dx times dx by dt. But then they gave us additional information. So we're given that x is -1, so we're going to go ahead and plug that in. We get a result there. And they also gave us dx by dt, which is 4. Right? So then we could just crunch the number at that point. So -14 plus 5 is what? -9 times 4 is a -36. Copy. Okay. All right, let's see if that works. So we got a -36 there. Okay. You're not gonna let me see my tabs and things. I know I got another window open. Okay, that's fine. Generate. I guess I'll pull it off for now. So I'll just let that be a separate window. I think we got 8. Let me just hit it one more time. We'll do 12. Okay. Come on. You just refuse to cooperate. Okay. 12. Okay. So find all antiderivatives. This comes from 4125. Okay. So we're working on question 12. This comes from section 4.1, question 25. Okay. Basically, they're asking us, let me see, we're given f of x equals e to the -12x. We're asked to find, we want the integral of f of x dx. Okay. So that's going to be the integral of e to the -12x dx, right? So it's going to be, it's e's integral is itself. It's going to be e to the power of -12x, but we got to say divided by the coefficient, so it's divided by -12, plus some constant of integration. Okay. And again, we can check if we take the derivative of this guy is going to be itself times -12, and they're going to cancel, and we get the desired result of the blunt. Okay. Okay. So then fraction, this is e to the -12x over, or we could move that negative, but that's fine, plus some constant of integration. Okay. Yeah, I got it here actually. Generate. I think we did 4, but let's see. Oh, okay, so if we did 4, we'll do 5. All right, I'm finding my way. Okay, so question 5. This comes from section 3.9, question 13. Given this y, find dx by dt when y is 6 and dy. Okay. So we're given y equals the square root of x. We're asked to find dx by dt when y equals 6 and dy by dt equals 1.75. dx by dt, they gave us dy by dt. Okay. So, all right, let's do it like this. So if we were to consider dy by the derivative of y with respect to t, we would have to take the derivative of y with respect to x first. Then we would say times the derivative of x with respect to t, right? I think we're trying to find dx by dt. So let's plug in what we have. So then dy by dt is 1.75 equals dy by dx Okay, so let's find the derivative of y with respect to x. The 1/2 comes down and we subtract 1. So it should be 1/2 x to the negative 1/2. That's dy by dx. And we're still trying to solve for dx by dt. Right? And they also gave us that x is, or it gave us that what, y is 6. Okay. So if y is 6, does that mean that x is 36? All right, from the original, because the square root of 36 gives us 6. So I'm going to put over here to the side, if y equals 6, that implies that x equals 36. Okay, so I'm going to plug in 36. So ultimately, our dx by dt should be 1.75 divided by, we got 36 to the power of a negative 1/2 times a half, right? Let's just crunch that real quick. So square root of 36 is 6. So that's 1 over 6. So that's really 1 over 12. So then that's going to be 12 times 1.75, right? I just kind of did it quickly. I think if you just kind of think about it, you'll see it, right? Maybe don't try to do exactly what I did, but you know how to find the square root of 36. You know what a negative exponent means, right? So just crunch this. You should get like 1 over 6. So then a half times 1 over 6 should be 1 over 12. Then we divide by fraction, keep change, flip, you'll get here, right? Hey, Google, what's 12 times 1.75? 21. Okay, so that was an interesting one. Let's see, dx by dt looks like it's 21. Let's try 21. Okay. Let's do another one. Let's look at question 12. So that's 4, 5, 6, 7, 8, 9, 10, 11. Looks like we did 12 already, so we'll go ahead and do 13, the next one. Okay. 13. This comes from section 4.1, question 31. All right, so just basically find the integral. So we're taking the integral of 5e to the negative 0.2 x dx. Okay. So with e, we were saying it's its own integral, so it's going to be like 5e to the negative 0.2x. But then we got to divide by that a, so divide it by a negative 0.2 plus some constant of integration. Type in exact answer. We could say a negative 5 over e. I'm going to type it like this. If it marks it wrong, I'm going to shift some things around. Okay. So on top, we have 5e to the power of negative 0.2x, negative 0.2x. And then in bottom, we have a negative 0.2. And over here, we have plus some constant of integration. Okay. Paste. Okay, so hopefully we're all aboard and we're not all bored. All right. Let's just kind of keep going. Again, just stop me if anything isn't clear. We can talk about it. Let's see. We got a generator over here. Generate. All right, let's do question number 1. Okay. So then question 1. This comes from section 2.2. Wow, this is a throwback. Throwback. 2.2, question 15. Question 15. Okay, we're just taking the derivative. Looks like the chain rule, right? So I'm going to say find dy by dx. And we have this y equals the square root e to the x plus 20. Okay. So dy by dx equals, if the power comes down, it's going to be a 1/2 times the inside times the radicand. We subtract 1, so that's going to be a negative 1/2. Then we got to say times the derivative inside function, which is just going to be e to the x. Okay. So essentially that first factor is on the denominator, the second one is on the numerator. Okay. All right, so on top we got e to the power of x. On bottom we have 2 times the square root e to the power of x plus 20. Okay. Right. This is fine. I can see it. Let's look at question 23. So that's the second to last. Okay. Do we have everything shown? Just about. Now this comes from section 4.1, question 65. I'm not sure what BE stands for. Business economics, maybe? I'm not sure what BE stands for. The rate at which a machine operator's efficiency, E, expressed as a percentage, changes with respect to time is given by dE by dt is 30 minus 10t. That's fine. So t is the number of hours the operator has been at work. Find E of t, given that the operator's efficiency after working 2 hours is 72%, that is E of 2 is 72. Okay. And then use the answer in part A to find the operator's efficiency after 3 hours and 5 hours. Okay. So we're given dE by dt equals 30 minus 10t, okay? And we're also given that E of 2 equals 72%, okay? So let's look at the integral of this 30 minus 10t dt, okay? The integral of a constant is the constant times t. The integral of t is going to be t squared over 2. So that's going to become 5t squared, like that. We're going to say plus some constant of integration. But then we're given additional information that E of 2 is 72%. Okay. So we're going to capture that like 30 times 2 minus 5 times 2 squared plus some constant equals 72. So then from there, our constant is going to be 72 minus 60 plus 20. Let's see, that would be what? A 12, so then 32. So then our, long story short, the E of t looks like it's right there. Let's do it like this. Negative 5t squared plus 30t plus 32. Okay. And then we could check by taking the derivative. Let me see. If I take the derivative, that's going to be a negative 10t plus 30. Okay. And then also when t is 2, that's a negative 20 plus 60 is 40. We get 72, which is correct. Okay. So this satisfies the derivative and the initial condition, E of 2 equal to 72, so we can be confident in this. And from here, it wants us to evaluate the efficiency after 3 hours and 5 hours. So then B, we want to calculate the efficiency after 3 hours and 5 hours, right? 9 times 5, that's a negative 45 plus 90, so that's just 45 plus 32, 77% efficiency. And then E of 5, what is that, negative 125 plus 150 plus 32. That's 25 plus 32 is 57% efficiency, which is what you would anticipate, right? The longer you work, the less efficient they would expect you to be. So these numbers make sense at least. Okay. So then E of t, we're getting negative 5t squared plus 30t plus 32. Okay. After 3 hours, 77. And after 5 hours, we got was 57. Okay. Ho, ho, ho. I don't know why I keep having us do question 4. Let me look. So let me see, 1, 2, 3, 4, 5. Let's go ahead and do question 6. I think that was just going to be 16x plus a constant. We've kind of done that several times over today. Let's look at question 16. That's 14, 15, 16. Solve. The answer can be determined by rules of antidifferentiation, but some algebra may be required beforehand. Okay. So this is question 16. This comes from section 4.1, question 84. Let me see. We have this u to the power 7 minus 3u to the power 4 plus 5 over u to the power 4 du. We're taking the integral of this guy. Okay. So again, I think earlier I mentioned something where I said if we're dividing by a monomial, then we can distribute that monomial, right? And maybe it'll make it easier. So we can try it. So then we can rewrite this guy as 7 minus 4 is going to give us u to the power of 3 minus 3 plus 5 u to the power of negative 4. So now if we take the integral, the first term is going to be u to the power of 4 over 4 minus 3u. Let's see, this is going to be minus 5u to the power of, sorry, not 5. Yeah. Let's see, if we add 1, it's going to become a negative 3 over 3 plus some constant. I'm going to submit it like this and see if it works. If not, we can like move some things around. So then the first one is u to the power of 4 over 4 minus 3u minus 5u to the power of a negative 3 over 3 plus some constant. Okay, let's see if they'll accept this. Okay. All right, gentlemen, are there any other burning questions before we go our separate ways? Paste. Okay. Let me make a copy of this available. I want to share. Send it to Box. '24 traditional calculus notes updated daily. Yeah, it should be right here. 25, which is 4.1 is correct. So when this bar finishes loading, you'll receive a copy of anything that you saw me writing. And if there aren't any burning questions, we're going to go ahead and end the session here. On Wednesday, we'll pick up with section 4.2. Enjoy the rest of your evening, gentlemen, and take care. Peace.
Hi, Professor. Have a good one.
Take care. See the chat real quick. Yeah, I got you. Yeah, it's okay. I take attendance as I let you guys in. So as long as you make it into the Zoom, then you got your attendance credit. So, hey, gentlemen.